Hello everyone. So in the last class, we started to talk about the Kolmogorov hypothesis. We built a framework for where this can be described. We talked about the energy cascade. We talked about how the rate of dissipation is dependent on the rate at which energy is transferred from the large scales to the small scales, because that happens to be the first step in the process of energy cascade. So you would think that the rate of energy dissipation is dependent on the rate of energy transfer from the large scales to the small scales. And then we related it to the simple formulation of rate of energy over time, which is U0 cube over L0. Turns out it is independent of kinematic viscosity. So what does this all mean, isn't it? That's where we are going with this. So the first question we need to answer is, okay, so there is dissipation that is independent of viscosity. Now, the first question we need to answer is, what is the size of the smallest eddies that are responsible for dissipating the energy? What is the size of the smallest eddies that are responsible for dissipating the energy? So as L is decreasing, as your length scale is decreasing, so do the characteristic velocity and time scales UL and TL, or tau L actually. Do they increase, decrease, or remain the same? That's the question, isn't it? Two questions here. What is the size of the smallest eddies that is responsible for dissipating the energy? One. And second is, as the length scale is decreasing, what happens to the velocity correspondingly? What happens to the time scale? So let's try to answer these questions by going over the Kolmogorov's hypothesis. Kolmogorov formulated three hypotheses based on the theory that UL and tau L, as in U of L and tau of L, decrease as L decreases. So the velocity decreases with length scale, and the time scale also decreases with length scale. The first point, in general, the large eddies are anisotropic. What does that mean? They have a directional dependence. That's what anisotropic is. Isotropic means they have no directional dependence. They are directionally independent. And I am talking about statistics. I am talking about statistics of the fluctuations. So what we are saying is that the first point here is that the large eddies are anisotropic. They have a directional dependency. And Kolmogorov argued that the directional biases of the large scales are lost in the chaotic scale reduction process. So as the length scales get decreased, as the large scales get broken down into smaller and smaller scales, that directional dependence, that directional biases are getting lost further and further. And as the energy is being transferred from the large scales to the smaller and smaller scales, they are tending to be more isotropic. It started with large scales which are anisotropic, but as the scales get broken down into smaller and smaller scales, it is losing the directional biases and becoming more and more isotropic. This is what leads us to Kolmogorov's first hypothesis of local isotropy, which is what? At sufficiently high Reynolds numbers, the small scale turbulent motions are statistically isotropic. First point I want to make here is, you will see in all these hypotheses, one of the first things we need to state is that the Reynolds number is sufficiently high. As in, it is fully turbulent. It is not, so this hypothesis might not be entirely true if the Reynolds number is moderately high. It has to be very high. It has to be sufficiently high. Otherwise, this hypothesis may not be true. It gets truer and truer. That is what Kolmogorov argued. It gets more true. It gets truer and truer as the Reynolds number increases. So every hypothesis starts with this phrase, at sufficiently high Reynolds number. Otherwise, this may not be true. So what is the first hypothesis? At sufficiently high Reynolds numbers, the small scale turbulent motions are statistically isotropic. So they are directionally independent. The anisotropy has gone away. They are directionally independent. Now, with that being the first hypothesis, let's introduce a new length scale and let's call that LEI. Okay? For example, it could be of the order of magnitude as L0, quite close to L0. And for now, I am arbitrarily going to say that it is approximately equal to 1/6 L0. In fact, there is a reason why we are using the 1/6. We will see that in the later modules. For now, just consider that as an arbitrary number. I am saying that it is 1/6 L0, an arbitrary number. So it is of the same order of magnitude as L0, but it is close to L0, less than L0. And let's say this LEI is the demarcation between the anisotropic large scales and the isotropic small scales. So L greater than LEI are anisotropic and L less than LEI are isotropic small. Isn't it? We always wondered how do we differentiate, how do we demarcate between large scales and small scales? Well, I am saying right now that let's say there is an LEI which is 1/6 L0. And above 1/6 L0 it is what we call anisotropic large, and below 1/6 L0 we are saying they are isotropic small scales. Because according to Kolmogorov's hypothesis, okay, you have the anisotropic large scales which get broken down into smaller and smaller scales, and those small scales are isotropic. That is what he's saying, statistically isotropic. And let's say those are below 1/6 L0. So what Kolmogorov argued is that by the same reasoning as what we presented earlier, the geometry of the large eddies determined by the mean flow and the boundary conditions is also lost. What do I mean by that? So when a flow is coming into a jet, if I show you a jet flow, a turbulent jet flow, you will be able to identify that it is a jet flow, because you will see that the flow is coming out of the nozzle and it is getting spread out into a jet. You will identify that it is a jet flow. When I show you flow in a channel, I'll show you the two plates, I'll show you the flow coming into the channel, you will be able to identify just by visually looking at it that it is a channel flow. When I show you flow over a cylinder, I show you the flow coming over the cylinder, you will be able to identify that it is a flow over a cylinder. That geometry is not lost. You are identifying the geometry. The boundary conditions is clear. The mean flow is clear. However, what Kolmogorov is saying is that as the scales get broken up into smaller and smaller scales, that information about geometry is lost. Meaning, a simple way to put it is that if you zoom in into a jet flow, if you zoom in into the domain on a jet flow, so if I have something like this is the jet flow. Now clearly, as I'm looking at this domain, I can realize that this is a jet. But if I zoom in here into this domain, I cannot identify whether this is a jet flow or not. If I zoom in on that location, I will see that there are a lot of scales here. And that does not tell me whether it is a jet flow. Same thing goes for channel flow. So this means that, Kolmogorov argued that this means that the statistics of the small scale motions are in a sense universal. You don't know whether they are from a jet, you don't know whether they are from a channel, you don't know whether they are from flow over a cylinder, so on and so forth. So in that sense, they are very similar in every high Reynolds number turbulent flow. The small scales, not the large scales. Clearly, if I show you a jet flow and a channel flow, you will be able to tell me what is a jet flow and which one is the jet flow and which one is the channel flow. But if I zoom in, the argument of Kolmogorov is that if I zoom in and show you just this part, zoomed in here, you will not be able to identify whether this is coming from a jet or whether this is coming from a channel flow. That's what we mean by the small scale motions are universal. similar in every high Reynolds number turbulent flow. So now, what is the second point? Now, on what parameters does this statistically universal state depend on? On what parameters? So now we know the first hypothesis told us that we have these large scales and the small scales. There is a demarcation. We identified a demarcation, arbitrary to begin with, but we identified a demarcation. And we said that the small scale motions are universal. Now, what does this statistically universal state depend on? The two dominant processes are, one is the transfer of energy from the large scales to the small scales. So the rate at which energy is transferred, I am going to call that TEI. It is the rate at which energy is transferred. And the second dominant process is the viscous dissipation. So I have the transfer and the dissipation. These are really the two processes that govern the energy cascade. The transfer is the first process and the dissipation is the last process. The dissipation at the small scales obviously depend on the kinematic viscosity. Now, since the transfer is the first step in the energy cascade process, epsilon is determined by the transfer rate. We said that earlier. Epsilon is determined by TEI. So epsilon is of the order of TEI, which is the rate at which energy is transferred from the large scales to the small scales. So how do we answer this particular question? On what parameters does this statistically universal state depend on? So that is where Kolmogorov's first similarity hypothesis comes, which is his second hypothesis. It is his first similarity hypothesis. His first hypothesis was related to statistical isotropy at the small scales. His second hypothesis, which is his first similarity hypothesis, is as follows. In every turbulent flow at a sufficiently high Reynolds number, see, we always have to precede the hypothesis by stating the fact that it is at a sufficiently high Reynolds number. The statistics of the small scale motion have a universal form that is uniquely determined by nu and epsilon. That is determined by viscosity and dissipation rate. So what he is saying is that you have these anisotropic large eddies above, say, 1/6 L0. You have these isotropic small eddies that are universal, and they depend on two dominant processes in the energy cascade. The first step, which is the transfer, which is what dissipation depends on, and the last step, which is the dissipation at the small scale, which depends on viscosity. So essentially two things, viscosity and dissipation. That's his first similarity hypothesis. Based on this, the Kolmogorov scales can be defined as eta, u eta and tau eta, given as follows. So eta is nu cube over epsilon to the 1/4, u eta is nu epsilon to the 1/4, and tau eta is nu over epsilon to the half, purely by dimensional analysis, something like a Buckingham Pi's theorem. We have shown this earlier in one of the earlier modules, but this is where it is coming from. Kolmogorov's first similarity hypothesis. He argued that the statistics of the small scale motions, the isotropic small eddies, have a universal form that depends on nu and epsilon. So if it only depends on nu and epsilon, you can derive small scales that are shown like this. Eta is nu cube over epsilon to the 1/4, u eta is nu epsilon to the 1/4, and tau eta is nu over epsilon to the half. Now, two identities can be derived from this, and this is also something we did earlier. The fact that Re eta, that the Reynolds number associated with these small scales. Now, this here are what we call the Kolmogorov length scale, the Kolmogorov velocity scale, and the Kolmogorov time scale. They are named after Kolmogorov. What he called as small scales, or what he called in his paper as the smallest scales in turbulence. length, velocity, and time. They are now named after him. So the Reynolds number associated with these small scales is of the order of 1. So eta u eta over nu is 1, which is consistent with the notion that as you proceed to the smaller and smaller scales, the Reynolds number is sufficiently small. You have a sufficiently high Reynolds number to begin with, and now it is sufficiently small. And 1 is like the smallest whole number, isn't it? So here you have a Reynolds number that is small enough that viscosity takes over. So the use of the number 1 is arbitrary. We're just trying to say that it is a Reynolds number is very small. And we are saying that, okay, you pick the smallest natural number 1, and that's an easy relationship in order to move forward. Now, so that's the first thing. The second identity is what? So you have eta equal to nu cube over epsilon to the 1/4, and u eta is nu epsilon to the half. So if I take u eta over eta, okay, what do I get? I'll substitute my relationships. So the nu epsilon to the 1/4 divided by nu epsilon to the 1/4 and divided by eta, isn't it? So nu cube over epsilon to the 1/4. So this becomes nu epsilon and then an epsilon from the bottom divided by nu cube to the 1/4. So then what I have is epsilon to the nu over half. Now, if I look at what tau eta is, it is nu over epsilon to the half, isn't it? Nu over epsilon to the half. So what I'm saying is u eta over eta is tau eta. U eta over eta is 1 over tau eta, isn't it? Based on these two relationships, which again is consistent. Think about it. You have, what we are saying is that velocity over length is 1 over time, which is consistent again. So that is what we mean by this, showing that if u eta over eta is 1 over tau eta, then that means our relationships that we have just shown here are consistent. So they provide a consistent characterization of the velocity gradients. So two identities, isn't it? The first one is that the Reynolds number at these scales, Re eta, which is eta u eta over nu, is equal to 1. And that can be obtained by just multiplying these two equations. If you just multiply these two equations, you will get that to be equal to 1. So that's your first identity. Your second identity is that what we showed is that u eta over eta is 1 over tau eta, which is again, both of these identities show what? They show that the Kolmogorov scales correctly characterize the smallest dissipative eddies. Because we showed that the Reynolds number at these small scales is 1, and we showed that the velocity scale, the smallest velocity scale divided by the smallest length scale gives you 1 over the smallest time scale. So what this is showing is that these Kolmogorov scales characterize the smallest dissipative eddies. That is what these two identities are showing. So now let's consider a point x0 in the highest, in a high Reynolds number turbulent flow, right? At time t0. So a point x0 at time t0. In terms of the Kolmogorov scales at x0 t0, you can get non-dimensional coordinates, and let's call that y, and you can define it as x minus x0 over eta. So what we are doing is we are scaling it with the Kolmogorov scale. And you can thereby also define a non-dimensional velocity difference. So let's call that W, which is U minus U divided by U eta. So as much as you are taking the difference between the velocities, you're also dividing it by the Kolmogorov scales. Here you divided it by the Kolmogorov length scale, here you divided it by the Kolmogorov velocity scale. Now, according to the hypothesis stated above, what we said is that the small scales are statistically isotropic. What we said is that the small scales are universal, that depend only on nu and epsilon. In that case, what we are saying is that when Wy is examined on a not too large of a scale, meaning if it is less than the energy demarcation length scale, it is statistically isotropic and statistically identical in all high Reynolds number flows. This is what we are trying to say. If you scale it with the Kolmogorov scales, if you scale the length scale and the velocity scale with the Kolmogorov scales, we are saying they are statistically identical. And again, we are examining at length scales that are not too large of a scale, meaning they are less than LEI. Okay, they are less than LEI. Obviously, since we are scaling everything with the Kolmogorov scale, we are saying that it is less than LEI over eta. So that is what this means. So on the small scales, all high Reynolds number turbulent velocity fields are statistically similar on the small scales, and they are statistically identical when they are scaled by the Kolmogorov scales. So the small scales have a universal form that are similar, isn't it? But if you scale it with the Kolmogorov scale, what we are saying is they are statistically identical. So two hypotheses according to Kolmogorov, right? The first one was that you have these anisotropic large scales and you have these isotropic small scales that are statistically isotropic. His second hypothesis was the first similarity hypothesis, which is the fact that the small scales have a universal state that depends only on epsilon and nu. And we extend that by saying that these small scales are statistically similar, isn't it? Because they have a universal state. And if you actually scale it with the Kolmogorov scale, they are statistically identical. So in that sense, the ratio of the smallest to the large scales are readily determined by the definition of the Kolmogorov scales. And from the scaling epsilon, which is equal to U0 cube over L0. So this we derived earlier. So here, this is where I want to show something. So if you have epsilon, which is of the order of magnitude of U0 cube over L0, because remember, this is a dissipation, isn't it? Which is the rate of energy transfer with time. So what we are saying is that energy dissipation rate is the rate of energy transfer with time. And that is how you get U0 cube over L0. So now if you take your Kolmogorov scale, you have that as eta. Okay, you have eta, which is of the order of magnitude of nu cube over epsilon. So in fact, this is the definition: u cube over epsilon to the 1/4. So what that means is eta to the 4th is nu cube over epsilon, isn't it? And you have epsilon being equal to U0 cube over L0. So if I take U0 cube over L0, now I'll equate the epsilon from here to the epsilon from here. And then I have U0 cube over L0 is equal to nu cube over eta to the 4th, isn't it? So that means eta over L0. Eta over L0 would be equal to nu cube over U0 cube eta cube, or eta to the 4th over L0 to the 4th is equal to nu cube over U0 cube L0 cube. So what does this mean? So eta over L0 is approximately equal to Re to the Re to the minus 3/4 because Re is U0 L0 over nu. So this is how we derived it. So the smallest length scale to the largest length scale is Re to the minus 3/4. That came from your definition of the dissipation rate, which is U0 cube over L0. So that is how we get this particular equation. So keep in mind what we have shown is that the smallest length scale to the largest length scale is of the order of magnitude of Re to the minus 3/4. So when Reynolds number increases, the separation between eta and L0 keeps increasing. The gap widens as Reynolds number keeps increasing. We will show that for U eta over U0 and tau eta over tau 0 as well in the next class. But I hope the hypothesis is clear. Just to reiterate, his first hypothesis was that you have these anisotropic large eddies and then you have these isotropic small eddies. So they are statistically isotropic. His second hypothesis, which is the first similarity hypothesis, is that you have the isotropic small eddies have a universal form. You couldn't know whether it is a jet or a channel, isn't it? They have a universal form that depends only on epsilon and nu. And they are statistically similar and they are statistically identical if you scale it with the Kolmogorov scales. So I hope that was clear. In the next class, what we'll do is we will derive this particular relationship as well and go on to the Kolmogorov's next hypothesis. Thank you.